Hello and welcome back. In the last video, we covered the Fundamental Theorem of Calculus Part 2. If you're worried about skipping out on Part 1, don't worry. That's what we're going to cover in this video. Let's take a look at the velocity function. So here's v of t. Again, t is along the x-axis, velocity is along the y-axis. And here we're going to consider the area under that velocity function from t equals 0 to t equals x, where x is going to be a variable. And in fact, in the picture, you can see there's a little dot right here. So you can imagine taking that dot and just dragging it over to the right. And that's going to change the area of the velocity function. What it's going to do is give us the area so far as we're moving x to the right. So this area, though, as we mentioned, represents the change in position over that time interval. It represents that distance traveled, or that change in position over that time interval from t equals 0 to t equals x in this case. So that area here, note, is going to be a function of x. It's going to depend on what x is. The bigger x is, the bigger the area is. Let's write up this relationship between the area under the curve, which is what the integral represents, and the change in position from t equals 0 to t equals x. So the integral would be the integral from t equals 0 to t equals x of the velocity curve. That represents the area under that curve. And all that work we did in the last video was to realize that area, that visual area, represents the distance traveled, or in other words, the change in position, which in this case is the position at t equals x minus the position at t equals 0. Now what we're going to do is play around with this just a little bit. We're going to differentiate both sides with respect to x. WRT means with respect to x. Note that s of 0 is a constant. So when we differentiate s of 0, we're just going to get 0. Well, we'll write the derivative with respect to x on the left. I'll put some parentheses around here. Looks okay. And on the right, again, derivative of s of 0 is 0. The derivative of s of x is the derivative of s of x. So we can write s prime of x in that case. But if we think about s prime, the derivative of the position function, well, that's the velocity function. So another way we could write this is like this. Keep the left side the same. But on the right side, we could write v of x, right? S prime is v. Derivative of position is velocity. In general, this works for any function. It's not just velocity. This works for any function. There wasn't anything special about that velocity function. So in general, the derivative of this integral, this special integral, and here I'm going to put, instead of 0, I'm going to put a right here. Notice that it didn't matter that we had the starting t value of 0. No matter what constant goes in here, s of that constant is a constant, and the derivative of that will be 0. So it doesn't matter what our starting t value is. So in general, if we take the derivative of the integral here, the derivative of this integral, in a sense they're undoing each other, and you just get back the original function. They're undoing each other. A way of thinking about this is here, if you think about the integral from a to x of f of t dt, that's like the area so far. That's the area so far. If you take x and you're thinking about dragging it to the right, so there's some kind of motion where you're dragging it to the right, this represents the area so far. And if we take the derivative with respect to x, it's representing the change in that area function as you drag that right endpoint to the right. And the change in that function depends on the function values directly. The rate at which it's changing is equal to the function values. it kind of makes sense in the picture here. You can think that, like, if you're going to move x over by just a little bit, you're going to have to paint on another layer of area. And that layer of area is going to depend directly on the function value. And in fact, it's going to be equal to that function value right there at x, at t equals x. So the rate at which the area function is changing, the rate at which you're painting on more area to the right, depends on the function values. Depends on, well, in general, f of x. In this specific case, our function was v of t, or, well, v of x, actually. V of x is the velocity at that x value. And so that gives a little bit of an intuitive understanding of what this is saying right here. And what this is saying is exactly what the Fundamental Theorem of Calculus Part 1 is saying. It says if we've got a continuous function on a closed interval, and big F of x represents that area under the curve, so area under f from a to x, from t equals a to t equals x. So it's like the area so far function where x is a variable that you can change. So that function then would be continuous on the closed interval from a to b and differentiable on the open interval. And its derivative, its derivative is little f of x. So if we took the derivative of that integral, we would get back to little f with an x plugged in. Or you can think again, it's the rate at which this area function is changing is going to be equal to the function values on the right side of that area. Let's see what this looks like in the examples. Let's see what this looks like in action. So here we have y equal to this integral from a to x of t cubed plus 1 dt. Now the key thing to note here is that this is a function of x. It's a really funny way of writing a function, a funny looking way of writing a function, but this is a function of x, right? T cubed plus 1 has some antiderivative. We don't have to know exactly what it is. And at the end, we would be plugging in t equals x, then put a minus and plug in t equals a if we were to use the Fundamental Theorem of Calculus Part 2. And so eventually this would be some function of x. And so then our goal here is to use the Fundamental Theorem, in other words, the Fundamental Theorem of Calculus Part 1, to find dy dx, in other words, the rate at which this is changing with respect to x. So here's how it looks. Dy dx, the rate at which this function is changing with respect to x, is the rate at which that integral is changing with respect to x, the rate at which that area there, which the integral represents, is changing with respect to x. And there's your little, let's see, here's your little f of t. And what the Fundamental Theorem of Calculus says is that the derivative undoes this kind of integral and gets you back the original function, but instead of having a t inside, it'll have an x inside. So right here, we're going to have the original function, the t cubed plus 1, but instead of a t, there's going to be an x plugged in. So we'll get x cubed plus 1. And that is it. It's a really short problem when you know that Fundamental Theorem of Calculus Part 1. Okay. So the second example, we have the integral from x to 5. So here, it's not exactly in that form that we need it to be in to use the Fundamental Theorem of Calculus Part 1. But here's where our properties of definite integrals can come in. We know that we can switch the limits of integration, and that flips the sign of the integral. So let's do that, and then we'll put the x up on the upper limit, where we can then use the Fundamental Theorem of Calculus Part 1. So what we can do is write dy dx, which is the derivative of the integral from x to 5 of 3t sine t dt. Again, we can't use the Fundamental Theorem of Calculus just yet, but we can use it after we flip the limits of integration, 5 to x, and then flip the sign. But instead of putting the negative sign right here in front of the integral, I'm going to take it out and put it in front of the derivative. We can do that because constants can be pulled out of derivatives, like that -1 that's pulled out. So there's the negative, and then here we can use the fundamental theorem. So once again, I'll write, here's our little f of t, and then our big f of, little f of x will be over here, 3x sine x. It's like the same thing as the little f of t, but just with an x instead of a t. Okay. Now the next example, the problem is not that the x is on the bottom, but that instead of an x, we have an x squared on the top. So what to do there? Well, it turns out that what we can do is a substitution. We can let u equal x squared. You get to be x squared today. Lucky you. We'll let u equal x squared. Now our goal is still to find the derivative of y with respect to x, right? And now we've just rewritten y in terms of a new variable u. Now y is a function of u. It's not a function of x anymore after we make the substitution. But still, y is a function of u, but then u is a function of x. So when we want to take the derivative of y with respect to x, find the rate at which y is changing with respect to x, we can use the derivative, the chain rule, to help us break it down into the derivative of y with respect to u times the derivative of u with respect to x. Because we have y as a function of u right here, and then u as a function of x, so we can break it down into the derivatives of those two individual functions. This is by the chain rule. Okay, so the derivative of y with respect to u will look something like this. It's d du of, oops, let me put this in parentheses, d du of the integral from 1 to u cosine t dt. Now du dx, well, that one's pretty straightforward because here's u equals x squared. Du dx will be 2x. Now here, once again, we have a good setup for the fundamental theorem part 1. Here we have the derivative with respect to u of this function of u, and where the function is written up as an integral from a to u. So this is like some number, some constant number to just the letter u. And we're taking the derivative with respect to u. And so the fundamental theorem says, well, these two are going to undo each other, and you'll just get f of x, little f of x. But since we're not dealing with x right here, our variable is u, so it's going to be f of u. Cosine u in this case. There's little f of u. Now the only last thing is to go back to x. U was just a temporary variable we were using. And there we go. So the rate at which this area function is changing with respect to x is 2x cosine x squared. Let's try one more. Here we have two problems. One is that our constant's up on top, our variable's on the bottom, and it's not just a letter x on the bottom, it's an expression in terms of x. So we've got a little bit of work to do to straighten all this out. So there are two things we have to do. One is flip the integral, flip the limits of integration. Let's do that first. So flip the limits of integration, we'll put 4 on the bottom, 1 plus 3x squared on the top. We have our negative sign out in front, because when you flip the limits of integration, you flip the sign. And then we're going to let u equal 1 plus 3x squared. Okay, so now we're ready to find dy dx. Once again, we'll use the chain rule because we've got y as a function of u and u as a function of x. And I'm going to go ahead and put the negative symbol that's in front of the integral that would go here. I'll put it outside of the derivative, so we'll stick it out here. And we've got 1 over, let's see, 4 to u, 1 over 2 plus et. And then the du here looks like 6x. I'm going to go down. I'm scared if I go to the right, I'm going to run out of room. Probably still run out of room going down. All right, so we have negative, and then by the fundamental theorem, oops, there's our little f of t. By the fundamental theorem, the derivative with respect to u and the integral from 4 to u here, they're going to undo each other, and you'll just have f of u here. So instead of a t, we're going to have a u. 1 over 2 plus e to the u times 6x. There's our f of u. You don't have to write those little notes down at the bottom there, although you do want to write your substitution. That's important for a reader to know about. This little f of t and little f of u is just for you to follow as you're connecting this with the fundamental theorem part 1. So the last step here would be to combine these together and go back to u. Go back to x. 1 plus 3x squared. That's using that relationship that we set up between u and x. Okay, so thanks so much for watching, and see you in the next video.